distance 3 times greater than the height. As we shall see, all of the simple machines achieve mechanical advantage in this same way, by trading force for distance. Consider the screw, used as a fastener in innumerable products and devices, but also found in many other interesting places. Like this corkscrew. This automobile jack. And even in the rotating blades of a modern snowblower. In all cases, the purpose of the screw is to convert rotational motion into linear motion, or to convert a rotational force, which we call a moment, into linear force directed along the length of the screw. Now, a moment is defined as the tendency of a force to cause rotation. If I place my wrench onto this bolt head and then apply a 1-pound force to the handle, like this, I'm applying a moment to the bolt. Its magnitude is the force, 1 pound, times the distance from that force to the center of rotation, about 6 inches. And therefore the moment equals 6 inch-pounds, or 1/2 foot-pound. By the way, in this situation, when a moment is applied to a rotating shaft, it's also called a torque, a term we'll be using often when we discuss automotive technology a few lectures from now. So how does a screw change a moment into a linear force? Well, first, it always requires 2 matched sets of threads, one moving and one stationary. With this nut and bolt, both sets of threads are actually manufactured. There's a set of male threads on the bolt and a set of female threads on the nut. With this lag bolt, there really only is one set of threads manufactured into the device. However, the bolt itself cuts the second set of threads into the wood as I drive it inward. In either case, the bolt's angled threads translate the applied moment into a larger longitudinal force. This force drives the lag bolt into the wood, and it clamps the nut and the bolt head tightly against the connected material in the case of the nut and bolt. Now, in this sense, a screw actually works much like an inclined plane that's been formed into a cylindrical shape. And if you don't believe me, let's just wrap this inclined plane around this shaft. As we do, I think you can see where we're heading. The end result looks very much like a screw. Visualizing the threads of a screw as an inclined plane also helps us determine the mechanical advantage of the screw. If we visualize the screw as being rotated by a tangential force moving around the circumference of the shaft, like this, then the distance through which the force moves corresponds to this horizontal edge on our inclined plane. And the distance through which the screw actually moves corresponds to this vertical edge of the same inclined plane. Now, since mechanical advantage is always about trading force for distance, the theoretical magnification of force by this particular screw is exactly equal to the ratio of the large length divided by the smaller length. That is, this length divided by this one, which happens to be 2.75 for this particular screw. Most screws and bolts actually have their threads oriented on a significantly shallower angle. And so their theoretical mechanical advantage is actually much larger than 2.75. But I emphasize the word theoretical because the usable mechanical advantage of a screw is always substantially reduced by friction. All machines, simple and otherwise, are susceptible to this problem, of course. But the screw's performance is more dramatically affected by friction than most machines because the longitudinal force on the shaft clamps the surfaces of the moving and stationary threads so tightly together. A metal screw typically loses over 80% of its theoretical mechanical advantage to friction. Yet this isn't necessarily a bad thing. Thanks to friction, screws and bolts are said to be self-locking. I might be driving this lag bolt into the wood, but then when I remove my wrench from the lag bolt, it doesn't spontaneously unscrew itself, as it would if there were no friction between the threads. Now, not all simple machines are self-locking. Levers typically are not. And, for example, if I return to my inclined plane and I pull the cart up the plane, but I remove the force, the uphill force from that wheeled cart, well, certainly it's going to roll back down the inclined plane. However, I can make this ramp self-lock